Look at some important definitions which are very useful while studying or while solving the problems using backtracking. So the first one that comes in our mind is explicit constraints, which are mentioned explicitly. So examples of explicit constraints may be uh, like this, that there is xi which is greater than or equal to 0, or you may say that si is the set from where the constituents of your solutions are to be chosen, and si in itself contains all non-negative real numbers. In the same way, the second one, it may be 0 or 1, or it may be belonging to a set of containing 0 and 1 only. So nothing so specific about explicit, means which are given, which are provided to us. You may consider the domain of different variables, different domain of different input and output variables, that is to be considered as your explicit constraints. The one of the example is for your n queens problem. So we know that the solution is going to be a vector containing the values of x1, x2, x3 and x4. So we cannot have more than 4 values. So it is the explicit constraint number 1. It means its length is going to be 4. Now the second one is this x1 can have the value from the set 1, 2, 3 and 4. And same is the case with x2, same is the case with x3, same is the case with x4. So all these xi's may have, or you can say xi is belonging to the set 1, 2, 3 and 4 only. So this is again one of the explicit constraint for your n queens problem. Fine. So the explicit constraint depend on the particular problem instance I of the problem being solved. All tuples that satisfy the explicit constraints define a possible solution space. So the new term here is the solution space of I. So what exactly we mean by it? He says that let us assume that we were solving the 4 queens problem. The solutions were tuple containing x1, x2, x3 and x4, and the possible solutions for this may be 1, 1, 1, 1, 1, 2, 3 and 4, then 2, 2, 2, 2, then and so on. Means all these are going to be the probable solutions based upon just the explicit constraints, or you can say just the outcome of the application of explicit constraints. Because what were the explicit constraints? That these all may have the values from the set 1, 2, 3 and 4. So just by applying the explicit constraint, we are having a solution space. And how many tuples are going to be there? 4 raised to the power 4 or n raised to the power n tuples are going to be there in the solution space for this problem. So we may very easily say that the application of explicit constraint results in result in your generation of solution space. Fine. Now let us this 4 raised to the power 4 tuples are represented as nodes. Okay. So these all are nodes. Each node specifies a tuple like this. Fine. So this all is termed as your solution space. And one of the way of generating this solution space is using your trees. How? We started with the node number 1, then we are having 4 options as per having our explicit constraints, means 1, 2, 3 and 4. Fine. It means queen number 1 could be placed in 4 columns, and queen number 2 again may be placed in 4 columns. Then queen number 3 again was able to be placed in 4 columns, and queen number 4 was again. So these are the roots, these are the nodes of the tree. Fine. Now the last level, this one, this constitute your solution space, or you can say this is the representation. The last level is representing this 4 raised to the power 4 nodes. So it is very much problem specific, that at which level and what are the various nodes which are defining, which are representing your solution space. So this is the last level is our solution space and is containing 4 raised to the power 4 number of nodes. So any solution based upon any program, any algorithm design methodology targets this. Out of these 4 nodes, we need to come up with the one which is satisfying the criterion function. Fine. So the next term in the line is our implicit constraint. I just informed you that the solution, the tuples which are satisfying the criterion function must follow the implicit constraints, or you can say implicit constraints and your criterion function are the same thing. So the implicit constraints for your n queens problem are: number one was no two queens should be following each other row wise, no two queens should be following should be, you can say, facing each other column wise, no two, and the third one is no two queens should be facing each other diagonally. So these three were your implicit constraints for your n queens problem. We may go through the definition also. The implicit constraints are the rules that determine which tuples in the solution space. Solution space कौन सा, ये जो हमने that we have just represented above. Determine which of the tuples in the solution space of I satisfy the criterion function. And this is the criterion function, or you may say that criterion function and implicit constraint are one and the same thing. Fine. Does the implicit constraint describe the way in which xi's must relate to each other? Fine. Now just try to observe one thing, that the application of each implicit constraint, the application of implicit constraint results in decreased solution space. Can we say this? In the problem of 4 queens, this one, the 4 queens problem was having 4 raised to the power 4 nodes in the solution space, this one. Now if we apply the first two implicit constraint, which are those, if you apply row wise and column wise constraint, or you can say implicit constraint, if these two are applied, then we'll be able to have a reduced solution space. How? Now look at this diagram, this tree. In this tree, what we did is that we have just considered the row wise constraint and the column wise constraint. Means to say that when we started placing first queen, the x1 was having 4 options. Done. X1 was having 4 options. So these 4 options means the queen will be placed here, here and here. Done. Now if x1 was placed and we moved, or we are searching for placing x2, then we know that as x1 was placed in some row, that the same row just not be used for placing x2. It means we will be having only 3 options for placing x2. So these are the 3 branches, denoting those. Now when we moved for finding the place of x3, because we already know 2 rows were already containing queens, so only 2 rows are left. Fine. So it will be having 2 branches only, and while placing x4 we will be having the single branch. Just try to observe that just by the application of these 2 implicit constraints, we are able to reduce the solution space size, which was earlier of 4 is to the power 4 nodes. Now it is of 4 factorial, isn't it? It is of 4 factorial, means 4 is to 3 is to 2 is to 1. 4 3s are 12, 2s are 24. So only 24 nodes are going to be explored for the possible solution satisfying all the implicit constraints. With the application of each implicit constraint, the size of your solution space is going to decrease. Just assume that along with these two, we also applied the diagonal constraint. then definitely this 24 is further going to be reduced. Now the next definition in the line is state space tree. State space tree. So very simple definition for this is that the tree representation, the tree representation of solution space is called is called the state space tree. State space tree. So the tree in front of you is a kind of a state space tree only. Fine. Why state space tree? Because it is representing. It is representing. It is representing all the states which are present in the solution space after application of your two implicit constraint. Fine. And the tree that I drawn in initially, this one, this tree is also a state space tree. State space tree which was representing or which was showing all the nodes or all the states which were there when we considered only explicit constraints. Fine. So this is the definition for your state space tree, that the tree representation of your solution space is called as your state space tree. Now there are certain more definitions. The first, or you can say the second one in the line, is your problem state. Problem state. So what exactly it is? Says that each node within the state space tree, each node within the state space tree is a problem node, or you can say problem state in itself. So all the nodes from 1 to 65 are problem states. Fine. Now the second definition is the solution state. Solution state. Solution state is a state as such that the path from root to that state S forms a tuple of your solution space. So we already know that the solution space of your 4 queen problem was a tuple that was containing some value of x1, x2, x3 and x4, isn't it? So the solution was of this form. Now just observe this tree, that the node number 5, the path from root to node number 5 is x1, x2, x3 and x4 are the values. So for node number 5 the path is going to be 1, 2, 3 and 4. For 6, node number 6 or 7, you may say 7, this one, the path is going to be 1, 2, then 3 and 1, like this, 1, then 2, then it is going to be 4 and then 3. So it is going to be 4 and it is going to be 3. In the same way you can generate the paths from all the nodes. After generating the paths, you will observe that the states which are only at the last level are going to form such tuples which are there in the solution space. So this is the definition for your solution state, that all the states S for which the path from root to that state S forms a tuple that is there in the solution space. So this is our second definition, or you may conclude that only the leaf nodes of the state space tree are going to form your solution state for n queens problem. It is very much problem specific. The next definition is the answer nodes. Answer nodes or answer state. Answer state is a solution state is a solution state which satisfies all the implicit constraints. Implicit constraints, or you may say, is a solution state which is a part of the solution tuples. Solution tuples. So better is to say that is a solution state which satisfies all the implicit constraints, or in turn satisfy the criterion function. One and same thing. Fine. So in this tree, some of the states from the last level, some of the states from this level must be satisfying the three implicit constraints, which were the row wise constraint, the column wise constraint, and the diagonal constraint. So all those states which will be satisfying these implicit constraints will be termed as our answer states. So our overall purpose is to start from the root. Our overall purpose is to start from the root and to reach to the answer states. Fine. And backtracking is a method which provides a systematic way to do it. To do this. Fine. So these are some definitions. Now let us discuss some of the techniques which functions to achieve, or you can say to get the solution once your state space tree has been generated. So we are now at a level that state space tree has been generated. There are two approaches. One is backtracking and the second one is branch and bound. However, it is not in the syllabus of CC 4 SEM. Now we already discussed what exactly is the backtracking. Just try to recall it for your 4 pins problem. So we generated a node. Done. Then there were 4 children for this node. So this was child number 1, this was child number 2, this was child number 3, this was child number 4. Okay. Now we explored this node. Done. And then we inserted all these 3 nodes in the stack, or you can say these nodes are yet to be visited, and we traversed, or we moved to generate the children of this node. So again there were 3 children. This was first, this was second, this was third. Again the same thing. These 2 nodes are to be put in the list of nodes to be explored further, and we just started exploring this node. Again this was generated and one of the node was pushed in the list of nodes to be visited. Now when this methodology is followed, then this is termed as your backtracking. Fine. What exactly is happening? We are generating the children, and we are picking one of them as the current node and pushing all others onto the stack, and then we further are exploring the current node and repeating the same process till we reach to the end. Now the second approach is that we generated the root, we generated its child number 1, then we explored it, then we generated the child number 2, we explored it, we generated the child number 3, then again we explored it, we generated the child number 4, then we again explored it. Once this exploration of this level is done, then we move to generate its child's node, its child's children. Fine, the children of this node. These are to be generated like this, and again we'll be exploring this one, then this one, then this one. Once this is done, we'll be exploring the options for this one. We'll explore this, this, and this one, and in the same way this. It means it is following the breadth first order, BFS, while your backtracking is following the depth first order, depth first search. So this approach is called your branch and bound, and the left hand side denote the functioning of your backtracking approach. Done. So in the next few minutes we are just going to define it more technically. Okay, so we are going to look at some definitions. So number one definition is your live node. What exactly it is? So live node is a node which has been generated, but all of its children have not been generated. So this is called as the live node, a node which has been generated, but all of its whose or all of its children have not been generated is called as the live node. The second definition is your e node. E node. So e node is a live node whose children are currently being generated. Fine. The third definition is the dead node. Dead node is a node which is not to be expanded further. Just like your B labeled nodes in your 4 queens Statespace tree, or whose or all of whose children have been generated. So any one of these condition, if it is there, then we'll say that a node is dead. Fine. Now we'll try to define or you can see we'll try to give a technical definition to our backtracking and branch and bound approach. Fine. So let us try to assume that while solving 4 queens problem, we generated the first node, and then there were 4 children for this. Done. So we generated this one. So this was the live node at that time. Fine. This was the live node. And now when it's children, this one is generated, it becomes the e node. Fine. So this is the live node, this is the e node. When 3 of its children are supposed to be generated, so this is going to be generated, this is going to be generated, this is going to be generated. Now we know that when this one is generated, so it will become the e node. Means we are going to look at this, and this node will become the live node. Means it has already been generated, but all of it, means this one is not generated yet, this one is not generated yet, because we choose the first child as the new node, and then we generated the children of this e node. Now when this was generated, so this become e node and this become your live node, because this one is still left. So this is the concept behind your backtracking approach. Was exactly it says is that as soon as new child C of an e node R is generated, then the child node C becomes the new e node. Fine. Okay. And R becomes the e node only when the node C is fully explored. Fully explored. So this is the technical definition for your backtracking approach. And now try to write it for your back branch and bound approach. So if you try to define it, then we'll say that E node remains the E node until it is dead. Until it is dead. Or you can say that we generated this one, then the first child was explored. Fine. Then the first child was explored. This was the E node. Fine, because its children are being generated. This was explored, then it was generated, then it was generated, then it was generated. So it remained the E node throughout the process till it is dead. And when a node becomes dead, when all of its children are explored or it is not to be explored further. So these are the few definitions for your backtracking approach, and you may differentiate using this between backtracking and your branch and bound approach.